Just for funsies, I'm going to start the recording and include this fantastic YouTube video that I found. Goat babies in pajamas. Why not? There is actually audio in the clip. It'll be in the recording, but not in the live session here. Ah! This one's got like strawberries on its pajamas. What? Yes! Good times. Huh? Huh? What? They just love to run around. Okay, we're supposed to start, but the clip's almost over. It's got like 5 more seconds. Okay. All right. Okay, that's good. Let's move that over. And yeah, let's say some things here. Round of announcements. First off, it is Wednesday, April 22nd. Happy Earth Day. Quizzes Tuesday and Thursday, so meaning there's a quiz tomorrow. Please keep current with web work, and what that means is, since it is April 22nd, I would strongly suggest starting web work number 37 today. Office hours are still available, and if these times don't work, please send me an email. Let's set up a time to meet at some other time. Happy to meet at some other time. Office hours can be done by WebEx or by phone in case you need another option for the audio link. And then as for like the written aspect of things, an option that's not WebEx could be sharing of the same Google Doc and both typing into that. So I'm trying to be creative and give you some options for how to join office hours and that sort of thing. Let's just take a moment to briefly review the. Hang on a second here. I got to do one thing. Let's take a brief moment to review the process of the substitution thing that we saw yesterday. But what I want to do is I'm going to change up the language just a little bit. So this is the same idea as yesterday, but I think because now we've seen some problems, going into even slightly more detail can be clearer. I was afraid of saying it this way yesterday. Step one would be to pick u. So u equals something, and I left this blank here. And well, that's because it depends on the problem you're looking at. And the major hint for picking u is if you see the derivative of u somewhere else in the problem, then this is usually a good choice for what u is. It doesn't always work out, but that's kind of my go-to. I think of what's in these parentheses. That's sort of the key sentence I think of as the hint that helps me out. Then you compute the derivative, and instead of calling it u prime, it's helpful here to call it du over dx. And then solve for dx. Actually, that process of solving for dx first always involves multiplying both sides by dx, because in step 2, dx was in the denominator. And then here's step 4 is where I'm slightly rewording it from the way we said it yesterday, because now I think it's a little more helpful to say replace blank. That means this spot is filled with whatever you had up there. And so replace that with u, and also replace dx with what you just solved for in step 3. And then you're looking for cancellations to occur. That's what's supposed to happen in general. It doesn't always work out. So if all the x's go away, that is, yeah, so all of the old variable x is gone and you only have this new variable u. That's good. The substitution was successful. If that doesn't happen, you're going to have to try something else. Maybe you have to go back and pick a different u, kind of back to step 1. And these things take trial and error. So when this is new, I think you kind of have to try some u's and see what it feels like getting stuck. It's an art form more than it is a science, unfortunately. So you've kind of just got to try getting stuck so that you know what that feels like, and it helps you build your intuition for how you should guess what u is better in the future. It's strange, but it really does work out that way. So you got to be willing to get stuck. My point was sometimes what has to happen is if this substitution wasn't successful, sometimes you go back and you pick a different u. Sometimes, though, substitution isn't the method to be used. So before we started substitution yesterday on Tuesday, on Monday and then last Thursday, we had done integrals anyway without substitution at all. So just directly integrating, meaning, thinking about what's the antiderivative. Anyway, um, yeah, I'm just step five is it's not even really a step so much as it's a check. Like, do you have all the x's gone and only u's? If not, then go back to step one. Try again. If so, then move on to step six. So then do the integral that has just u's in it. So if we really pass step five, so there's no more x's, do the integral. And what I mean by this phrase, do the integral, this is the one that seems to get people. So that's why I've included this additional language: is find the antiderivative. Right? That's what this integral means: integral of or antiderivative of. So undo the process of derivative. And when you do that, please don't forget the plus c. And then once you've done that, and only once you've found the antiderivative, because that's, to be honest, the hardest step is step six. So once you've found this antiderivative, this problem only has u's in it, then you go back and now replace the u with, well, fill in the blank. And this fill in the blank is the same one up at the top in step one. It has x's in it, by the way. And that's why you don't want to switch the order in step 7 and step 6. This is the problem I usually see. So do the integral, step 6 first, before the final replacement of u. So step 6, then step 7. I've seen people do, and to now clarify even more than yesterday, I've seen people try to swap the order. So they'll do step 5, and the check is good, and then they'll make a replacement. But then the integral problem they have has both u's and x's in it all of a sudden again. And then to try to do the integral, that's messy because there's two variables. So don't swap the order. Don't try to combine the steps. Step 6 is challenging enough on its own. So why try to do step 6 and 7 at the same time? Like, people do this wonderful job I've seen, in previous semesters of doing step 1 and step 2, step 3 in order and doing one thing at a time. And then all of a sudden there's this strange mad rush to try to, finish the problem off and move, but people took it a step at a time, steps 1 through 5. Just, take it easy there with step 6, the hardest step. I don't think that's a good time to try to combine that hardest step with step 7. So just don't combine the steps. And then the other thing is don't skip. So I've seen people just do, all the x's go away, and then they don't bother doing an integral. There's this integral symbol that says find an antiderivative, so they won't at all. They'll just drop the symbol, not do any antiderivative at all, and then just replace the u. So don't skip step 6, and don't skip step 7 for that matter either, right? So don't steps 6 and 7, do them one at a time in that order. Don't swap the order. Don't combine the steps. Don't skip one of the two steps. Those are the usual problems that I see occur. So I'd like to go through the process. So yesterday's slides had a problem like this that we didn't get a chance to go through in detail. So this problem is not the same problem as the one at the end of slides yesterday. It's a problem of the same type, just so if you look back at those other slides, you'll have another example. So let's look at this. The integral of x cubed times the quantity x to the fourth plus 5, close parentheses, to the sixth power dx. So this integral, or we could say antiderivative of, I'm sitting here looking at this going, how am I supposed to find the antiderivative just staring at it? Like, the derivative of fill in the blank equals that. Don't know it. I don't know off the top of my head. So that's not the way I want to attack it. I'm like, maybe this substitution thing is what we need to do. Actually, I should point out there's a way to do this without substitution at all. So one option is to FOIL 6 times, right? To take this part right there and expand that out. That'll take a long time. And then once you've done that, only once you've done that, then you can distribute the x cubed into this bigger mess that's been expanded out. And then at least you have a bunch of separate terms. You'll have lots of them, actually, and then you can anti-differentiate one term at a time. So in principle, that's a way to do this problem. That seems very tedious, very time-consuming, right? It could take an hour to do it that way. So I don't want to do that. Instead, let's do a substitution. So I picked u equals x to the fourth plus 5. My thought process in picking that for u is that when you take the derivative of x to the fourth plus 5, due to the power rule, you'll have 4x to the third. So that 4 in 4x to the third, I'm not all that worried about. So the 4, we'll figure out something's going to happen with when you do du over dx, and you have 4x to the third. The 4, it'll somehow come in front of the integral in some sense. It won't actually be a 4 in front of the integral, but something like that. The key point is the derivative of u, this key part here, this x cubed, I see it elsewhere in the problem, right? So do you get what I mean by elsewhere? So there's where u is, and then elsewhere, somewhere else. So not in the same spot, but just right next to it. I do see that x cubed business. So other than the 4 part in the 4x cubed, I sort of morally see the derivative somewhere else. So that's why I went with u equals x to the fourth plus 5. And you might say, why the plus 5? It's because you often want u to include the constant. So this is better than just using u equals x to the fourth alone. The reason is the derivative of the constant 5 is 0. So staring at this u right over here, when you take the derivative, d over dx is 4x to the third. We need to solve for dx, so multiply both sides by dx. So you'll have du equals 4x cubed times dx, and then if you divide both sides, so sorry to do the 2 algebra steps on one, but I multiply both sides by dx, and I divide both sides by 4x cubed. That should end you up with du over 4x cubed equals dx. Are we okay so far? Just want to see before, I mean, we're certainly not done, but just want to kind of address, are we okay with the algebra manipulations, the derivative that occurred, the choice for u and why it was chosen, any of those kinds of things? Okay, then having done these steps here, and some of this is more commentary, right? That's how in-class problems look compared to when you're doing your own problems for homework later. Um, so there's the original question, kind of recopied, mainly because I wanted to. Well, I didn't have much room up here for one, and also it's I think helpful in the slides for you to see we had this discussion and now we're ready to tackle this question. So it does require a bit of rewriting, unfortunately, but now let's part of the reason to do this is to demonstrate the equal signs right away. So I make a replacement. I made two replacements. I hope you see. The x to the fourth plus 5 was replaced with a u. So the exponent 6 still needed to be copied. The dx was replaced with the fraction du over 4x cubed. So I hope that looks okay to everyone. Right? I replaced x to the fourth plus 5 with a u and replaced dx with du over 4x to the third. Now you'll notice that the x to the thirds cancel because there's an x to the third in a numerator and an x to the third in a denominator. There's still a 4 that's in a denominator though. So sometimes what happens is people kind of magically move a 4 up into the numerator. So 4 was in the denominator before. Just because you get the cancellations here, that doesn't mean that 4 should move into the numerator. So I wrote it as a 1/4, kind of near the front. Also, this du business was in the numerator of a fraction, but if you just kind of leave it outside of a fraction, that's kind of numerator quantity as well. So I think the thing is, other than canceling an x cubed on top and bottom, everything else was written here. It may just the order may have been shuffled, but stuff that was in the numerator before is still in the numerator. Stuff that was in the denominator before is still in the denominator. At this stage, this new problem has this setup, this look of, I think it was called step 5 earlier, where we check if all the x's go away, that was a successful substitution. That's what we have here, right? There's no more x's. It's just u's. So that's good, right? So with only u's, now we can talk about finding the antiderivative. If you swap the order, right, this thing I was trying to address a moment ago, the common mistake that people make is to, at this point, try to substitute the u with an x to the fourth plus 5. If you do that, I guess in principle, you technically get something that's valid, but it's messy because you'll substitute, x to the fourth plus 5 for the u. There's still the sixth power. And look at this problem. There's u there, and there's x there, and now you have to find an antiderivative? No, thank you. Right? So this is what I mean by it's the most common error. I see it a lot in 175. And so I just wanted to say, I just committed the error right now, right? Like, and it's, I don't know if it's so much well, Yeah, there's nothing technically wrong about writing this, but you're totally stuck at this point because there's a u, there's an x, and there's antiderivative of, and we have to find an antiderivative. I don't think it's worth it. I don't want to find the antiderivative there. What I want to do is look at this question right here, and let's now find an antiderivative. Right? So to find antiderivative, the 1/4 is that constant we get to copy. We've got to do this undoing of the power rule. So we have a u to the 6th. Remember, the power rule for derivatives lowers the exponent, so we need to raise the exponent. We'll have here copy the 1/4, and you have u to the 7th over 7 plus c. Okay, so this is the step that I'm talking about. Going from here to here is what I keep calling do the integral, or I'm also in parentheses, I keep trying to use the language find the antiderivative now as well to try to clarify what I'm talking about by do the integral. So having done the integral, you'll notice that this step doesn't have integral symbol anymore, right? We just found the antiderivative. And now that we've found the antiderivative, this is the step in which we now finally replace u with x to the 4th plus 5. Okay, so that's what finishes off the problem here. We're done with the question, but I will just mention that you could check. If you took this final answer, I wrote it down here in a little smaller print. If you take that and you differentiate, so differentiate this thing using the chain rule, it will result in this content up here. That's like right at the beginning. So that's worth checking. And also, I should comment, I made the comment yesterday, but it was not written down, but I want to mention, notice how hard it would be to replace the dx here. Right, dx got replaced with du over 4x cubed. Notice how hard it would be to replace dx if you don't write down dx in the first place. So kind of all of these kind of habit forming details are key. Good question came up. Why is it 1/3 and not Why is it 1/3 and not 1/4? Oh, that's because it's a typo. Thank you for catching that. Yep. Whoops. So I had taken yesterday's problem and started making some changes to it just to create a new problem on the spot, and I missed that one spot. So sorry about that. Okay. Um, cool. So thanks for catching that. Let's see. Now, okay, so that question done. Here's the other key point I guess I want to make is that uh, uh, sometimes this substitution thingy is not what you do. Sometimes what you do is you directly need to just integrate. So if you were given like this problem right off the bat, like let's say that was the circled problem there, let's say that was the Weber question, I wouldn't bother doing any substitution. I just look at the question and go, okay, I've got to undo the power rule. And so I say this because sometimes you have to use substitution and sometimes you don't, but no matter what, at some point, even if you do apply this new method, new as of yesterday method of substitution, you eventually need to find an antiderivative. So here on one side, I tried to organize all of the antiderivative rules we have so far. I hope I got everything here, that the antiderivative of x to the nth is x to the n plus 1 over n plus 1 plus c. We just used that in the previous question. That applies as long as the exponent isn't a negative one. If the exponent is a negative one, then the antiderivative is ln of absolute value of x plus c. We saw this rule for exponentials that the antiderivative of b to the x is b to the x over ln of b plus c. If you have a constant times a function that you're anti-differentiating, the constant can come in front, so you can just take care of the anti-differentiating the function alone. And pluses and minuses are very happy features for antiderivative. Their multiplications generally are not. I mean, if it's multiplication by a constant, cool. But when it's one function times another, you probably have to FOIL things out, something like that. Yeah, and here's the comment that I should have waited to say. I said it. Sometimes what you need to do is just apply one of these formulas directly without doing any of this u substitution thing. So sometimes I think what happens is because we have this new thing, all of a sudden every problem that people look at that has an integral symbol, people are like, oh, I got to figure out what u is. And sometimes it's not figure out what u is. Sometimes it's just apply one of these formulas directly without the u substitution thing, because I sort of think of it as like, oh, I guess I have to use u substitution because I have this terrible problem, like very complicated problem that I'm thinking of applying this u thing. But if I can get away without doing this u thing, maybe all I need to do is FOIL something out, and then the problem looks nice. Then I do it that way. Um, yeah, and then there's that just kind of word on notation again, kind of a repeat from yesterday and the day before, but I'm saying it a little differently here. Is that when you see this dx in the numerator, if it's helpful to you, just push it off to the side, kind of where the dx has been when we first presented it. And yeah, just a reminder that the integral of 1 over x dx is the integral of x to the negative 1 dx. That's an algebra step, right? And then this integral of x to the negative 1 dx, that's from up here, the second bullet point from up here, and I just copied that text right there. So what I want to do actually is I'd like to give you some time to work on these, and I'm going to stay on the line. All of these questions, all 8 of these require substitution. So if I start revealing a little bit in the slides, it'll just state what I think you should use for you. So I'm going to kind of hold off on advancing the slides and suggest what you do is try one of these. You don't have to go in order. I mean, you could 1, 2, 3, 4, 5, 6, 7, 8. But try one. Or if you just want to, like, before digging too much into the problem, you want to say, like, I think I'm going to use u as this. And you can unmute and ask, or you can type, and I will respond. Hope that kind of works as a thing. I just want you to practice the substitution thing. If you get stuck, fine. And I do have full solutions for you at the end of class as well, like handwritten solutions as opposed to typed solutions. But maybe just kind of pick one and go, and then they get more challenging towards the end. I should comment on that. just want to see how we're doing and see if, there's sort of like a, I think I should do this for this question, but I'm not sure. And if you're doing fine, that's okay too. But just wanted to check. Okay, so how about this? These slides do not show full solutions to the questions. If you want, well, if I advance the slide just like one moment forward, then you'll see it says try this for you. So each time it'll give sort of like the suggestion for what you should which you will work out. Let's put it that way, right? So maybe I'll just zip through this real quick, just so that so that you don't see that. The key I know that having run these questions in the past, that people want to see full answers, and is their work right. And this is the first semester in 175 I'm using slides, and I thought I had some handwritten solutions somewhere, but I couldn't find them. So yesterday I redid them, and I just want to show you where they are, if that's so. If you go to, I have open here Canvas, and when you click on the class homepage, you can find it in the home area, I believe also in modules, but there's this area where I'm trying to post all of the things that I normally hand out in class, and the most recent one is this PDF. So I'm going to click to open it so that you can kind of see in terms of format. I was tempted to just type the solutions into the slides, but then as nice and clean as slides can be at times, sometimes they're a little too clean. And I think the problem is like work sometimes looks a little different when it's handwritten versus typed. And so I wanted you to see what handwritten work for for questions like these really look like, because you're not going to be typing full on answers, like you. So so there's a question up there. I screenshotted it from the slides, and I'm showing you my work. And I mean, you don't have to write vertically like this, but I just chose to. And then I, worked out the first question there in full, and then the next question fit right there. So does that? I hope. You'll just kind of go back later and just kind of browse through these slides. Or sorry, not these slides, but this PDF. It's 3 pages. I fit the 8 questions into 3 PDF pages, and I think the key thing to try to do is like, when you see an integral symbol here in my work and you don't in your work, ask, wait, what so I want you to be very careful about going through these slides, and your work might not look identical, but I think the question I want you to keep asking yourself as you browse through this would be, um, uh, if I have an integral symbol, is it supposed to be there or not? Right? Where's the plus c appear? Did I anti-differentiate? Did I do things like combine steps when I shouldn't have, or swap the order of steps, that sort of thing? Now, I will, since I do have open this like space where I can write. If you'd like me to work one out fully just here while talking through it, I'm more than happy to do that. If instead you just want to kind of end class early with a little bit of a wrap up of things that I have here, a summary, that's fine too. So I don't know if there's like one from the list that you want to see completely worked out right now and talked through, or question 8. Yeah, let's do that. Integral e to the 1 over x squared. So integral, let me use a thicker marker here. Integral fraction e to the 1 over x. Wait, I think there was a 5 in front, I think. 5 e to the 1 over x squared dx. So my thought here is to make u to be 1 over x. The reason I want to do this is, well, we got to differentiate, but I don't want to differentiate 1 over x, not written like that. So before differentiating, I'm just going to make the choice to rewrite 1 over x as x to the negative 1, so that when I compute the derivative, d over dx, it's negative 1 x to the negative 2. Another way to write that would be negative 1 over x squared, right? So, sorry, let's clean this up because there's now 3 sides to the equation. So instead, how about I just write down here du over dx is equal to negative 1 over x squared. So as is usual to solve for dx, it's in a denominator currently. So I want to multiply by dx on both sides, and I'll have du is equal to negative dx over x squared. And then, oh yeah, we're solving for dx, so let's multiply by x squared on both sides, and you'll have x squared du is equal to negative dx. Now, having that negative sign by the dx is also not helpful. The students will usually be in the habit of dividing both sides by negative 1, which is fine. That undoes this times negative 1 that you see here. But actually, instead of dividing by negative 1, it's just a little more convenient to multiply by negative 1 on both sides. So you could just multiply by negative 1, because then you'll have negative 1 times negative 1, and you'll just get a dx there. Cool. So the process of solving for dx in this question was quite a bit more involved. But now we can go back to the original question here. Integral. Oh, I should pause. Are we okay with that? Sorry, I don't want to rush. I'll just rewrite the question here in sort of the, just to make use of time as I ask, is all of this stuff kind of okay over there? Okay. So then let's substitute some things, right? So substitute anything we can. Our goal is to have a problem that used to have x's but now only has u's. So integral 5 e to the, that 1 over x is what we'll replace with a u. So with a u right there. In the denominator, There's an x squared. I'll just leave it as x squared for right now. And then there's a dx, which over here we see gets replaced with negative x squared du. Now, as written, this looks a little funky because to me this looks like minus x squared. I don't want multiplying by negative 1 to accidentally be confused with subtraction, so I think it's actually helpful to put a set of parentheses here. There is an x squared on top and bottom that cancel, and that's good. So we're left with a minus sign. I'll just stick that minus sign in front. Negative 5 e to the u du. Oh, this is great because there's no more x's. If you cancel x squared on top and bottom and just juggle, put the minus sign kind of in front, then the minus 5 could even come completely in front. Integral u e to the u du. And this should be negative 5. So to anti-differentiate now e to the u is its own derivative, therefore e to the u is its own antiderivative, just with a plus c. Now that the anti-differentiation is done, we can replace the u with, I forget, I gotta go back up here. Sorry, 1 over x. Sorry to scroll like this. I know it's a little less than ideal. This 1 over x, I'll make it a little smaller because it is an exponent. So that's the full problem. It's a challenging one, so sorry for. I felt like that was actually a little speedy, but I hope that's just part of this. Maybe this way is like you kind of. Of course, I've got a handwritten solution as well you can look at later, but it's maybe sometimes helpful to hear my thoughts about the question as well as. Okay, so what I'll do then is let me go back to these slides and just I want to summarize some key ideas here. We will look at more substitution tomorrow. You'll have a chance to practice different problems tomorrow, or I would, encourage you to, if you have a chance today, practice the rest of these questions on this list, or I'll, try them tomorrow in class as well. But I think the key ideas that I want to talk about here are, at some point you have to, you've got to do that integral that has a u, right? So you've canceled out all the x's. You have this new problem that just has u's. It is an antiderivative problem. And so at some point you have to do an antiderivative, right? So do that in this substitution method. You do that integral that has a u, that is find an antiderivative, and then afterwards substitute u. And substitute u the other way. Like earlier, it was something was substituted for u. Now you do u substituted for that something. And then sometimes, though, you'll do the integral. That is, you'll have to find an antiderivative, not applying this new method of substitution at all. So some problems don't require substitution. And then sometimes, in addition to just not requiring substitution, sometimes the problem that you have, it'll be easier to do if you just do an algebra step first. Maybe it's foiling. Maybe it's taking care of how a fraction is written so that you don't have fractions anymore. So I just want to remind you that we still have some methods from last Thursday and Monday of this week that don't require substitution. And sometimes that's the right approach. Like sometimes if you're like, I have to do substitution, then you get stuck on the problem. It's almost like introducing this new method. Sometimes people forget about the old method. And so that's one of the things we're going to try to address some more carefully tomorrow. That substitution isn't always the approach. Doing the integral, as I keep saying, kind of this phrase, here, there, I mean by that is also known as finding the antiderivative. So I keep using this phrase. I want it to make sense. This is the first semester I'm trying to make a stronger emphasis on what the heck that means, because I think people got confused by this. So just to help reinforce these ideas, I think it's helpful if you will say to yourself internally or think antiderivative of when you write this symbol, right? That will help that process out. So you're going to have a step that has this integral sign and either a dx, or maybe because you've done substitution has a du instead. And then you've got a step that looks like that, and then the next step after that would have neither. At that point, you have the plus c. So this is in that process of doing the integral. The step before doing the integral has this integral sign. The step after no longer does. When does that switch occur? It's when you're stating the antiderivative, when you're doing this antiderivative problem, or you're doing the integral. The method of u substitution, again, does not always apply. So it applies sometimes. Just key reminder again, there will be an online quiz that opens tomorrow. Please, if you can, start WebWork 37 today. And tomorrow's warm-ups are here, and that the comments about substitution doesn't always apply. That's what tomorrow's warm-up addresses. So we'll end early, unless you have questions. Do you want to stick around?